Okay, so we're learning about identifying and graphing exponential functions. So just to contrast with what we already know, you can predict the next number here. I mean, if we had a 1, a 2, a 3, you can see that there's an increase each time by a plus 1. So you can predict this would be a 4. And this one, it goes from negative 2 to 0, from 0 to 2. The next number you can predict would be a 4, because this has an increase every time of a plus 2. And when you have a constant rate of change, we say that relationship is linear. In other words, if we were to graph it, it would form a straight line. Let me just graph it really quick. If x was 1, y would be a negative 2. If x was 1, y would be a negative 2. If x were 2, y would be 0. If x were 2, y would be 0. And if x were 3, 1, 2, 3, y would be 2. And then there you have it. This is straight line. And that's why it's called linear, has the word line in there. And that's represented by the equation y equals mx plus b. But now we're learning about something different. We're learning about exponential functions. So in exponential, we still have the same increase of plus 1 down here. And you can still predict the next number. After 3 would be 4. But as y increases by 1, as x increases by 1, y increases by a factor, or multiple, of 5. So it goes from 5 to 25, from 25 to 125. What would the next number be? As you can see, we're multiplying by 5 each time. Here, I'll put in parentheses. Because we're representing exponents or powers. So we're multiplying by a factor or multiple of 5. And so the next number would be 625. If we were to graph that over here, exponentials look a lot different. If x were a 1, y would be 5. So if x were a 1, y would be 1, 2, 3, 4, 5, would be right here. But then the next one would be if x were a 2, y would be 25. All of a sudden, we're really leaving the screen here. We're going somewhere in this territory. But then if y were a 3, it'd be 125. It would go way beyond this paper, and it would keep going somewhere to up there. Okay, so if I said to graph it, it's only over 3 on the x-axis, so it would be very much a steep but curve. It would start to curve more and more as we go through this. And here's the thing, it would never touch the x-axis. It would always get closer without ever touching it. And that's called an asymptote. And that it'd be sad if it was a human relationship to always get closer and never touch. But these never touch the x-axis. It just gets closer and closer and closer. And that's what exponential graphs look like. They kind of are very steep. They curve. They never touch the x-axis. Okay. So when we are doing exponential graphing, it's in this format of not y equals mx plus b. It's not linear. It's y equals a times b to the x power. Remember, the exponent only influences what it's right next to, not the a that's also being multiplied to it. So some things you need to know about this. That y equals a times b to the x power. The x must be a power, and it must be a variable. Must be a variable. Excuse me a second here. The reason it has to be a variable is because if it's a constant, it's not going to allow us to choose the different numbers for the x. The b cannot be a 1. And the reason that's the case is if it were a 1, anything to the 1 power is always 1. I could put a 3 to the 1 power and it would still equal 3. Or I could put a 10 to the 1 power, it would equal 10. So you wouldn't see much change. It would just be, 3, yeah. So it would just be itself. And then it cannot be a negative. And the reason it cannot be a negative is think about what that would do to your graph right now. Because a negative times a negative would be a positive. But then a negative times a negative times a negative would be a negative. So if I did 2 to the second power, I would have a 4. If I do 2 to the third power, I would have a negative 8. And so graphing that would look more like a heart monitor. It would go up to positive 4 on a number line. And the next time we go down to negative 8, then we go up all the way to positive 16. Then we go down all the way to negative 64. And so it wouldn't really look exponential. So for that reason, the b cannot be a negative. So a couple examples of problems like this that we can work out. Let me grab some real quick. Would be something like this. Y equals 2x to the third. Now my question for you would be, is this exponential? Does it meet the requirements of y equals ab to the x? Well, the answer would be no. Remember, the exponent has to be a variable. In this case, it's not. So that would be a counterexample. What if I did one like this? Y equals negative 6x. Would that be the format of y equals abx? Well, the answer is no, because that's actually the format of y equals mx plus b. It's linear. It doesn't have an exponent. See how the x is it's large. It's not small like an exponent. So the answer would be no. What if I had y equals negative 3 to the x power? Would that one be exponential? The answer is yes, because it's in that pattern of y equals ab to the x. You say, wait a second, I thought the b can't be negative. Well, right, what's right next to the exponent isn't negative. The negative is the a. Remember, if the negative were counted, it would have to be in parentheses to count the negative as well. One more. What about y equals 9 times negative 5 to the x power? Is that one in exponential form? The answer is no. Remember, it's all correct except for the b cannot be negative. In this case, the b here, a negative 5, is a negative, so it's not an exponential form. Okay, one last one. I suppose we have time to do one more. Y equals 4 times 7 to the x power. Yes. Y equals ab to it's an exponent. It's not negative, it's not 1. It works. Alright, I hope that cleared things up.